Okay, so my name's Gemma-Louise Davies, and I'm doing my PhD with Professor Yuri Gunko. And my PhD is all about using nanomaterials for potential biomedical applications like magnetic resonance imaging, or MRI. But before we get into that, I just want to define what is a nanomaterial. Well, nano means something which is in the range of 10 to the minus 9 times smaller than a meter. But what does that really mean? It's just all numbers. If we look at this scale and we look at a tennis ball, if we think of the size of a tennis ball, it's approximately 100 million times smaller than the size of the Earth. So if we go down to nanoparticles in the end, nanoparticles can be as small as 100 million times smaller than the size of a tennis ball. So they're absolutely tiny. But why do we work with nanomaterials? Well, it's because as we descend down to the world of the nanoscale, properties of materials start to change. And it's these different properties which we can manipulate to our benefit. So the type of nanomaterials I make are called magnetic nanoparticles. These have great potential in biomedicine, in particular for magnetic resonance imaging, or MRI, a technique which is used for diagnosis and imaging of tissues in hospitals, and it's very widespread in modern medicine today. In general, contrast agents are used to improve image quality in MRI, and magnetic nanoparticles could have huge potential in this area, because they're strongly magnetic, but also because their unique properties, thanks to their nanoscale size, means that we can use lower doses in MRI. So this is a very attractive prospect, and of course, speaking of attractive, a lot of nanoscale magnets have this property called superparamagnetism, which is quite a mouthful, but I can help you out with this. All it means is that the magnetic nanoparticles only act as nanomagnets in the presence of another magnet. This is just a normal fridge magnet. So here are some magnetic nanoparticles, you can see there. If we put the magnet on top of them, they behave as magnets. As soon as we remove this, they no longer act as magnets. So this is hugely beneficial because it means they don't aggregate in the body, but it also means that we can manipulate them for uses within the body and to carry out certain tasks. So here we can see a couple of different types of magnetic nanoparticles that I've made using imaging techniques, microscopy techniques. On this side, we've got the magnetic nanoparticles with no other magnet present. And on the right-hand side there, we can see the nanoparticles when there is another magnet present. And you can see they align into these very, very long wires. And this is what makes them excellent for potential biomedical and, in fact, potential MRI applications. So far, we've taken some of these types of nanoparticles and we've actually tested them as MRI contrast agents. And we do this by injecting them into mice like this and simply monitoring them using MRI, and they show great potential. But as for the future, this part of my work really has the potential to change the way in which this area of modern medicine operates by providing new types of contrast agents, which not only give, or have the potential to give, better image contrast and image quality, but can also be used at lower doses. And in fact, it's a perfect example of some of the cutting-edge research, which is hugely commercially viable, as we've seen other ones tonight, which is coming out of CRANN and out of Ireland as well. Thank you.